Okay, so I think we've seen enough examples of Sturm Liouville problem that I can talk about the general theory now. Usually what happens in a PDE class is that they tell you the Sturm Liouville theory in the beginning, and since like they have totally no idea what the professor is talking about because they haven't seen any examples. But we have seen enough examples. Whenever we use separation of variables to solve a PDE, we end up with some eigenvalue, eigenfunction problem, right? And the simplest cases were something like y double prime plus lambda y equal to 0, right? Oh, often there's a minus here. And we had like 3 different conditions. So one was y of 0 equals to 0 and y of L equals to 0. And what were the solutions of these? Remember? Sine. We got sine n pi over Lx, right? So these were the solutions, and so these were the non-trivial solutions. The only time that this differential equation would give you a non-trivial solution was when lambda is n pi over L squared. Okay? Then it admits these solutions, and that was later used as building blocks for representing any other function as a linear combination of these things, right? And that one would be here where Q is 0 and P is just 1. It's the simplest case of the Sturm Liouville. P is 1 and Q is 0. You just have y double prime equals to negative lambda. W would be 1 as well. Negative lambda y. And you're solving this with alpha 1 as 1, alpha 2 as 0, beta 1 as 1, beta 2 as 0. So you have y of 0 equal to 0 and y of L equals to 0. Oh, sorry, this should be B. Oh, wrong. So this would be like trying to find a function defined from the interval a to b. So y is on a to b, and we're looking for continuous function from a to b, where p, q, and w are all continuous on a to b, and then you're trying to solve these questions. Now, when we were doing, so in the Neumann case, we had primes instead, and the ones that have just the primes, that will be where you have 0, 1, 0, 1. And you could also have a heat equation where one side is insulated but the other side is touching ice, so you might have like prime on one of them and the other one. That still could have been a, we didn't do that case, but that could have been another thing we could do. Okay. And then there's also another condition called Robin condition, where something like y of 0 plus y prime of 0, it should be 0, or you might have like 3 and 2, some coefficients in here. Those are called Robin condition. We didn't even touch on this one. We only did the Dirichlet and Neumann, right? So, but we could have done such a thing. It's just that the solutions become uglier, so we didn't get to do it. And right here, this is all it's saying is that you can't have both of them 0. Then this becomes a non-condition, right? If alpha 1 and alpha 2 are both 0, then it doesn't give you any condition. You have a question? No? Okay. Now then, when we were doing the wave equation on a disk, we ended up with Bessel functions, right? So what were the Bessel functions? They were solutions of x squared y double prime plus xy prime plus x squared minus yeah, u y lambda. Yeah.
Which is squared.
Well, so it eventually lambda turns out to be m squared.
Yeah.
Yeah. So from something squared. Or did we?
It is.
Oh, mu squared. We had the mu squared, right? Yeah, right. Yeah. Eventually, mu happens to be an integer. Right? Okay. So this was called the Bessel function, and the condition for this was, I forgot what the conditions were. This was the radial one. So the condition is that y of 0 has to be finite, and then at the end we had the Dirichlet condition with 0 at the boundary. So you needed to have y of L equals to 0. So y of 0 has to be finite, and y of L equals to 0. And the solution of this one came out to be y equals to jmx or jlx, jmx, where let's use n, jnx, where this is called the Bessel function of the first kind, and mu squared happen to be n squared. Right? So these happen to be our eigenvalues. Okay.
It's in the disk, right? It's on the disk, or
It's if you solve the wave equation on the disk, this is what you ended up with. And for this one is a bit hard to change to that format. To make this one look like that one, you first have to divide by x and rewrite it as like xy double prime plus y prime plus xy equals to mu squared over x y. Yeah, you write it like this, and then this part will now become like xy prime plus xy equals to negative mu squared negative 1 over x y. Was this minus or plus? I kind of forget.
It's minus.
Minus? Okay. Okay.
So mu squared becomes. What you put negative? Oh yeah. Wow.
Yeah,
Put
yeah.
a negative 1 over
Yeah,
x.
I need the minus there. Yeah. Okay. Well. Anyways, so this one, you can see again. It's in this format where px is x and qx is also x and wx is negative 1 over x. That's what we found out. Now this is, however, the boundary conditions are a bit different. It's because, see, for this one, we call Sturm Liouville problem a regular Sturm Liouville problem if px, qx, and wx are all positive on A to B, but then here we're trying to solve this from 0 to L, but at 0 this becomes 0, right? So this is actually a singular differential equation at 0. It admits solutions that goes to infinity at 0. So you can't ask for a value. The most you can do is I want a solution that gives you a finite value. I want a non-singular value at 0. So that's a little different than what this is, but still same kind of theory can be made to work in this case as well. And then lastly, when we were doing Laplace equation on the sphere, on the ball, we had the 1 minus x squared y prime, y double prime, minus 2x y prime, plus lambda y equals to 0. And we found out that the only time this is from -1 to 1, and the only time this gives you a non-singular value at both endpoints. So y of -1 is finite and y of 1 is finite, then this lambda has to be L times L plus 1, and the solutions became what's called the Legendre equation, right? So Legendre polynomials, PL of x. Okay. So that one, again, you can rewrite this part as 1 minus x squared y prime and then prime outside equals to negative lambda y. So this is the case when p of x is 1 minus x squared and q is 0, and the weight function, w is called the weight function, w is 1, right? Okay. And then we found out that, well, I didn't prove it, but I also said that these functions are orthogonal to each other. So if you have plx and pkx, you multiply them and integrate from -1 to 1, you get 0. Another one was, yeah, so I should have said that as well. In the previous case, the simple ones,
Heat equation?
yeah, in the heat equation when we had y double prime plus lambda y equals to 0, when we had the sign n pi over Lx, if I had this one and sine n pi over Lx, and you integrate it from 0 to L, what's the value when n and m are different?
0.
You get 0, right? So you get these orthogonality relations. And that was important because that allowed us to expand things as a series, right? So this allowed us to write down the free sine series. The other case we had the free cosine series. We had the Bessel functions, and so that gave us the free Bessel series. You can also talk about free Legendre series if you expand functions in this format. So what I'm trying to get at is that somehow, if you have such a Sturm Liouville problem and you solve them, you find the non-trivial solutions. First of all, you get discrete values of lambda starting from the lowest, and you have these discrete values so that you can number them. Okay. And because of this orthogonality, it allows you to take any other function as a linear combination of the solutions of the Sturm Liouville, which enables us to take any initial condition or boundary condition and represent them as some of these things. That's how we solve things, right? Yeah. So that's the property that this Sturm Liouville problem wants to know. So Sturm Liouville theory or Sturm Liouville problem in general says that here I have an equation in this format, and if I have such an equation, then with these boundaries, or you could have periodic or sometimes finite, for those cases you always have some kind of an orthogonality principle. You always have distinct eigenvalues, and the solutions, if you collect all of them, they're in some sense complete. That means any other function can be represented as a linear combination. In this case, since you have infinitely many eigenvalues, you can represent any function as infinite series of the solutions of this. Okay, and you get like various Fourier series, Fourier Bessel, Fourier Legendre, or Fourier. That's called eigenfunction expansion in general. Okay, and that's what Sturm Liouville problem is about. Okay, so I want to show you two things. One is that has something to do with this being the operator on the left side being something called self-adjoint, and another one where I want to show you the orthogonal property. Okay, so those two things I want to show you, and after that I'll move. It's okay. Yeah. After that I'll move on to the discussion about the generic eigenfunction expansion, why they work.